Hey guys, Mr. Backerberg here. In this video, we're going to look at combining trigonometric and algebraic functions. So in this example, we're going to look at combining our sine function with an x squared. And we're going to do some graphing on our calculator. We're going to graph out these four functions over the interval from negative 2 pi up to positive 2 pi. And we're going to check which of these functions seem to be periodic. Now we're going to go one at a time, so I'm going to start with my graph for letter A there. So we've got y equals the sine of x plus x squared. So I'm going to fire up my calculator. So in my y equals screen, I've got that first equation typed in, sine of x plus x squared. I'm going to go to my window. I want to go from negative 2 pi for my x min up to positive 2 pi for my x max. I'm going to make my y min start at negative 10, and I'm going to make my y max go up to 20. Now, one other thing that I should check before I graph this out is to make sure that I'm in radian mode. So I hit mode, my radians is highlighted, we're good, so I'm going to hit graph. So we end up getting a picture that looks something like this. So now we're trying to decide if this function is periodic. So we should be thinking to ourselves, these sine and cosine functions are periodic because they are waves that repeat themselves. This one doesn't look like a wave, so it's a pretty safe assumption that this one is not periodic. Then our second graph, for letter B, we're going to look at y equals x squared times the sine of x. So in my y equals screen, I've got the x squared times the sine of x. I'm going to adjust my window a little bit. I'm going to leave my x min and x max where they're at because that's our negative 2 pi and positive 2 pi. But I'm going to make my y min go down to negative 25, and I'm going to make my y max go up to positive 25. So I hit graph. Now we end up getting a picture that looks something like this. We're checking to see if this is periodic, so we're looking for this graph to repeat itself, and it doesn't, so this one is not periodic. For letter C, we're going to look at y equals the sine of x squared. So in my y equals screen, I've got the sine of x squared, being careful to put that squared on the outside of my parentheses because I'm squaring the entire function instead of just the x. I am going to adjust my window. I'm going to leave the x min and x max where they're at because that's my negative 2 pi and my positive 2 pi, but I am going to adjust the y min and y max. For the y min, I'm going to go down to negative 2, and for the y max, I'm going to go to positive 2. So I hit graph. Now we're checking to see if this function is periodic, so we're looking to see if it repeats itself, and this function does look like it repeats itself, so I'm going to say yes, this one is periodic. And finally, for letter D, we're going to look at y equals the sine of x squared. So this one's a very similar equation to what we had typed in, but now I need to put that squared inside of my parentheses because I'm squaring the x only instead of the entire function. Now I'm going to leave my window where it's at with the x min at negative 2 pi, the x max at positive 2 pi, the y min at negative 2, and the y max at 2. So I hit graph. So checking to see if this one is periodic, we're looking to see if it repeats itself, and it's got very similar behavior, but it's not an exact repetition every single time, so this one is not periodic. Now thinking about those examples, the only one that seemed to be periodic was the sine of x squared, and we can actually verify that it is periodic algebraically. So if we look at the function f of x equals the sine of x squared, and we want to look at f of x plus 2 pi, because remember, sines are typically periodic along a 2 pi period. So this would say the sine of x plus 2 pi all squared. But now this is a normal sine function inside of my parentheses. The squared doesn't have any real effect on the sine right now. So because sines themselves are periodic with a period of 2 pi, this plus 2 pi in there is actually not necessary. So then really we've just got the sine of x again, but that's being squared. And that's the exact same thing that we started with. This is our original f of x function. So this plus 2 pi in there really didn't make a difference in the function, algebraically proving that this sine of x squared is periodic. Now in this example, we're going to prove that f of x equals the sine cubed of x is periodic, and we're going to do that algebraically. So what I want to think about is f of x plus 2 pi, because a normal sine function has a period of 2 pi. So we'd really have the sine cubed of x plus 2 pi. Now I'm going to change how this is written. Now another way to write this is as the sine of x plus 2 pi all cubed. And what we have to remember is that a normal sine function is periodic with a period of 2 pi. So this extra 2 pi in there really is unnecessary because of the periodicity of a sine function. So then we've got the sine of x cubed, but we can really rewrite that with that power back on the inside. So we just get the sine cubed of x. So when we plugged in this extra plus 2 pi, we still got the same exact function that we started with, proving that this function is indeed periodic. And we can look at its graph to kind of visually show that it's periodic. So if I fire up my calculator, now in my calculator I have to be a little bit careful as to how I type in this sine cubed of x. So I've got parentheses around my entire sine function, and I'm cubing that whole thing. Now I'm going to adjust my window just a little bit. My x min and x max I've got at negative 2 pi and positive 2 pi. My y min and y max are at negative 2 and positive 2. So when I hit graph, we'll get a picture that looks like this, and we can see that it is repeating itself, so it is periodic. Now notice we had that sine cubed of x, and if we look at kind of what's happening around these zeros, around these x-intercepts, we can sort of see the makings of a cubic graph. So one more example I want to take a look at. We're going to look at adding a sinusoid to a linear function. So let's say we had the function f of x equals 0.5x plus the sine of x. And I want to look at this graphically to kind of describe what's happening in there. So I'm going to fire up my calculator. So in my calculator, I've got the 0.5x plus the sine of x plugged in. Now for the window for this one, I'm going to hit zoom 6, and that's going to get us to our standard 10 by 10 window. So we can see we've sort of got this sine wave, but it's tipped on its side. And there's actually a couple of parallel lines that run across the top and the bottom of our sine function. So now remember that function that we typed in was 0.5x plus the sine of x. So as far as those parallel lines, if I think about that 0.5x and what's happening with that, that line would actually run down the middle of my picture. So if I went y equals and I did 0.5x, that's going to run right down the middle of my sine graph. But because our sine has an amplitude of 1, that means that our wave goes up one space from this line, and it also goes down one space. So actually those parallel lines are going to be 0.5x plus 1 and 0.5x minus 1. So we can see those lines run across the top of the peaks and the bottom of the valleys of our sine function. And that comes from that 0.5x at the beginning of our function, and that comes from the amplitude of 1 as far as our sine function went. That's going to be it for this video. Thanks for watching.